Catalysts increase the rate of reaction but are not consumed in the reaction, right? So they come in as a reactant, go out as a product, and they speed the reaction up by lowering the activation energy. This causes a shift in mechanism. So an uncatalyzed pathway, you have a big hump. If you use a catalyst, it lowers the hump. So more molecules have enough kinetic energy to get over the barrier. So that'll speed the reaction up. Oftentimes when you add a catalyst, you change the mechanism. So instead of being a one-step mechanism, it's now a two-step mechanism where we have an intermediate made in one step and then used in the next step. All right, there are heterogeneous catalysts which are in a different phase than the reactants. For example, the conversion of ethene and hydrogen into ethane. This reaction is very exothermic, but it's really slow. Speeding it up using a platinum, a palladium, a rhodium, or a nickel surface. All right, so you use this surface area, and what happens is you weaken the hydrogen-hydrogen bond, and you weaken the carbon-carbon double bond so that you get more effective collisions between the hydrogens and the ethene. With a homogeneous catalyst, they're in the same phase, right? So for example, the aqueous phase. So we have ethanol being turned into ethene and water. Really slow unless you use H+, and then it really goes fast. So H+ ions enter the reaction by colliding into ethanol, and you make this intermediate. This very unstable intermediate then falls apart to form ethene, water, and H+. So notice, when I add these steps together, the intermediate cancels. And H+ ions come out the same way they go in. All right, so I make this intermediate where the water pops off and the H+ pops off. And H+ goes in as a reactant and comes out as a product. So it speeds up the reaction by changing the mechanism, making this very unstable intermediate. But the H+ goes in and then comes back out. Ozone depletion, CFCs, right? So chlorofluorocarbons are a way of getting chlorine radicals up into the air, right? So a CFC goes up into the stratosphere, it gets nailed by UV radiation, and a chlorine radical gets produced. So chlorine radical gets bounced off of that chlorofluorocarbon. This chlorine radical then slams into ozone to make ClO intermediate, which gets slammed by an oxygen radical to turn to chlorine and oxygen. So the chlorine radical goes into the reaction the same way it comes out. So it can go from ozone depletion to ozone depletion reaction. And it does it by lowering the activation energy. This intermediate that you make is much easier to be, much lower activation energy in terms of slamming an oxygen radical into it and going to oxygen than slamming the oxygen radical directly into the ozone. So I could slam oxygen into ozone in a one-step process, but that would have a very high activation energy. If I use the chlorine radical slams into the ozone to make the intermediate. The intermediate then gets slammed by an oxygen radical and then goes to products. So the intermediate's used in one step, burned in the second step. All right, so the first hump is making the intermediate, that's the slow step. And then the quick step is the oxygen radical slamming into the intermediate to go to oxygen and reforming the chlorine radical. Lower activation energy, faster reaction.